Okay, let's continue with LiDAR. So next, I want to introduce different parts or say components of a LiDAR system. So a typical LiDAR system includes a laser generator, a scanner, high precision clock to record time, GPS, IMU. These two components I mentioned before. I also mentioned the function of them. Data storage and management system. Um, this part is for, of course, for data storage, just like the name, and also the computer system um, connected to the sensor in the field can do some processing before getting back to the lab, to the office. And the GPS ground station, actually, this component is a part of GPS. Um, they are on the ground to help um, provide location information. Let's go through them one by one. Um, some of them are not part of geography, so I'm not going to go very deep, okay? And the first part is a generator of laser. This is actually a part of high energy physics. It's just far beyond the content of this course. I found this information online about how laser generators generate lasers. So I will provide figures here and also the information on the right. I'm not going to read them. And actually, I'm not expert in physics. So I will just leave this slide to you. Okay, so in order to emit laser energy, first you need to you need to produce, to create laser, right? So that's the first step of LiDAR system, of LiDAR sensing process, okay? And the frequency of laser used by LiDAR usually ranges from 50K to 200K um, pulses per second, which means for every second, there are 50K to 200K pulses emitted from a sensor. Okay, specific value depends on specific sensor, right? And the laser utilized by LiDAR systems usually ranges from ultraviolet to infrared. So ultraviolet around 250 nanometer, blue-green optical light. This is for bathymetry. I introduced this before, right? Near infrared is usually for high accuracy terrestrial mapping on the ground. Infrared for meteorology, like temperature and wind speed and the amount of cloud can also be detected by LiDAR. And the maximum power of laser is limited by the need to make them eye safe, a requirement for most applications. I want to do a little explanation here. Laser can be very dangerous to your eye system. If the power of the laser is pretty high and you're looking at a laser beam directly, your eyes will be burned, which means you will be blind. You will be blind. And if the laser is seeable, is visible, then it's fine. You can just avoid looking at it directly. If the laser is within a blue-green range, then you should be able to see a blue laser or a green laser. Then you should avoid looking at it directly. But if the laser is the laser is within ultraviolet range, or near infrared or infrared, you cannot see them with your eyes because that's beyond humans' ability, vision capability. You cannot see them, but you cannot see them, they can still hurt you. So the maximum power of LiDAR system, of the laser employed by LiDAR systems needs to be limited to a specific range to make sure that even those LiDAR pulses cannot be seen by people. They're still safe if you accidentally look at them, okay? So that's very important. The next term I want to introduce here about laser is called field of view, FOV, or footprint. It could be large, could be small. Okay, this is, for example, this bar here is a LiDAR beam. It has a specific, you can say thickness or footprint size. Okay, if the size is pretty small, we have multiple laser beams within this area. If the size is pretty high, is pretty large, the FOV of this beam is pretty large, then within the same area we have less number of laser beams. So should we use small laser beams or larger laser beams? Laser beam divergence from 0.1 to 1 milliradian, and small FOV for detailed local mapping, large FOV for complete ground sampling, which means that if we're using, say, small beams, small LiDAR beams, it's convenient for us to collect detailed information on the ground. If we use laser beams with larger size, we can use one single beam to cover larger area, but less detail can be detected by your by your sensing system, by your LiDAR system, because within a LiDAR beam, within a laser beam, there are multiple objects, and one beam can only provide one signal. So this signal includes the information of this tree and the building. You cannot differentiate them. But if you use smaller laser beams, each beam may only have the information of one object. For example, this beam only has the information of the tree. The other three beams, they have the information of this building. So more detailed information can be retrieved if you are using smaller beams. And this is the most important factor you should consider when you're choosing from smaller beams and larger beams. Another factor you should consider is called SN, signal to noise ratio. It is negatively correlated with FOV size, which means the larger the FOV size, the smaller the SN value. The smaller the FOV size, the larger the SN value. And we want a larger SN value because SN value is the ratio between signal and noise. We want stronger signal and weaker noise. When the signal is strong and noise is less, we have larger SN value. So smaller laser beams also provide better SN value, or you can say larger SN value. But usually, if a sensor can provide smaller beams, it's usually more expensive. You should know that because it provides better SN value and also provide more detailed information of the ground. Okay, so larger laser beams or smaller laser beams, right? You should consider this when you're trying to buy a sensor, buy a LiDAR sensor, or you're picking one for your application, right? And the next component I want to introduce here is called scanner. This is a scanner. It's a part of LiDAR system. There is a mirror here. It spins to project laser pulses to the surface. So here at the top of this scanner, this is the laser generator or signal generator. The signal will be shot to this mirror, and this mirror will control the direction that the signal will be shotted to the ground. This mirror here will spin to control the direction of the signal of the laser beam, right? Scanning angles are up to 75 degrees. You should know that it's not 180. This mirror cannot face exactly the left or exactly the right. There is a limit for spinning degree. Scanner measures the angle at which each pulse was fired. Okay, and also IMU, I mentioned before, it was for the detecting of the gesture of the sensor. I mean, the scanner and IMU together, they will have, I should not say this, they will measure the accurate gesture of the sensor and the direction of the pulse. Okay, and the scanner also receives reflected pulses from the surface, and reflected pulses are also known as returns. Yeah, it's obvious, right? Reflected signals, they are returning from the ground. So each reflected signal is a return. And later you will see that each laser beam can have multiple returns or single return. How is that? I'll show you later. But now you should know scanner is responsible for controlling the direction of the signal to the ground, and also responsible for receiving reflected signals or returns. And here, your altitude, and the altitude of the sensor also decides what you can say, the area or the size of the area or size of the region you can observe on the ground. If your sensor is mounted to a plane or to a drone that flies pretty low, right? You're flying along this blue line, and your sensor, or you can consider this as a laser beam, or you're just flying along this direction. Anyway, the red line is actually the laser beam shooting to the ground, right? If you're flying low altitude, the area you can observe on the ground is relatively small. But if you're flying pretty high, and here is the laser beam, and red line again is actual laser beam shooting to the ground, you will cover a larger area. Okay. And the GPS, yeah, I'll just skip this. You know what GPS do, and IMU, I have also introduced it before. A clock, like I said, because you need to accurately record the time, the shooting time of this, the time for shooting the signal and the time for receiving the signal. So you have to use a very accurate clock to implement that, to make that happen. And also, next, it's also important for a LiDAR system. It's called flight planning. Flight planning, which means when you are a scientist or you're somebody, say that, trying to make a flight plan for LiDAR system to observe a specific area on the ground, what factors should you consider? First one, fair weather is needed. I've mentioned that LiDAR is pretty bad at penetrating clouds, and a cloud is another form of water, right? So raining is also bad for LiDAR sensors, LiDAR signals. So you want to make sure that the weather is actually not pretty good. At least there should not be a visible cloud, or it should not be raining. And the missions are usually carried out at night because the environment surround the environment, no matter, especially for urban area, in the night is relatively simple, right? Clearer air, less air traffic, less interference from sunlight. Okay, so if possible, carry out in the night. Returns. Multiple returns can be received for each laser pulse fired from the sensor. I mentioned this before, right? I will provide more information later, but now just remember, for each laser pulse, there could be multiple returns. And modern LiDAR systems are capable of recording up to 5 returns for each pulse. of course, the more returns you can have for each pulse, the more expensive your sensor is, okay? And the scanning overlap, this is a must. More overlap is needed for steeper terrain and urban areas in order to avoid LiDAR shadow. Overlap means that the area covered by the sensor should overlap with each other. I will show you with figures, but before that, let me show you the concept of LiDAR shadow. And here is the LiDAR shadow. So here we have a very typical commercial area, right? Commercial area. So some buildings here, we can say there is a door, there is a window. This is a wall for two buildings, building one, building two. And here is the street, here is a pavement and curb. We have two cars. So this is a LiDAR image. But the problem is here is that on the other side of the car, there are two shadows. That's because the sensor, let me use a pointer here. The sensor was flying this direction, okay? So the sensor is shooting signals from this direction. And all those laser pulses, signals, will be reflected by the surface of the car. That's the reason why for this side of the car, we can measure the distance between the car and the sensor. That's the reason why we have white pixels. Each one has a specific value. But since these two cars, they have blocked laser beams, the other side of the car cannot be, of these cars, cannot be detected. So how to solve this problem? We can fly back and observe from another direction, right? So in the end, let me clean this, erase all. In the end, the trajectory of your sensor should be like this. Fly this way, turn around, and get back. So both sides of these cars will be detected. There will be no LiDAR shadows, okay? So when you're planning this flight trajectory, you need to make sure that there is overlap, this area, between this scan and this scan. So like this. So when you are flying from left to right, right? And when you finish the scanning, you make a U-turn and fly from right to left. There must be overlap between these two missions, or you can say two scans. Scan one from left to right, scan two from right to left. There must be overlap between them. And also there must be overlap between two images within what? Within the same scan. So this shaded area here is actually the overlap. Why do we need the overlap? There are reasons. And firstly, sometimes your image could be damaged, or there's something wrong with the sensor, or there's something wrong with the plane, and your data is damaged. If you only scan the same area one time, and it only appears in one image, which means there is no overlap. If this image is damaged, then you have no information about the damaged area, which is bad. Okay, so we always want to make sure that one area is scanned at least 2 times, which means there must be overlap. The second reason is that there must be something called, in remote sensing, is called a geometric distortion. in our images. And we want to do something called geometric correction to how can I say, to reverse the distortion. And we also need something called georeference to connect each point, each pixel in your image to a real world location. When you are doing georeferencing, when you are doing geometric correction, you need overlapped area as reference, which means this area appeared in at least 2 images. So you can find the same location in 2 images to create the relationship between a specific location in the real world and that location in your image. That's the reason why there must be overlap. Okay, and about the multiple returns, here is the explanation. So here is the sensor or the plane flying over to you, and here the pink area is the beam shot by the sensor, by LiDAR sensor. So this beam is traveling to the canopy of the tree and penetrate the canopy of the tree and arrive at the ground. I mean, during this process of penetrating, some of the signal will be reflected by the top of the canopy. Some of them will be what? Will be reflected by the middle of the canopy. And some of them, I mean, if there are 3 returns, the last part of the energy will be reflected by the surface of the ground, or what? The earth, right? So here, part of the energy was reflected by the top. It will return to the sensor firstly, and then second return was reflected by the middle of the canopy. Sorry about my mouse. There's something wrong with my mouse. So here we have some noise here. Ignore them, okay? And the last part of the signal was reflected by the ground. It will also return to the sensor. So if this is the case, the sensor should be able to receive 3 returns for 1 laser pulse. Okay? Okay, but you should know that not all sensors can do this. Most sensors, I would not say most sensors. Some sensors can only receive what? 1 return. That's maybe the return of the from the top of the canopy. Maybe the return from the surface of the earth, but not all 3 of them. And I mentioned before that currently the most powerful sensors can detect as many as 5 returns. Okay, but you need to know that they are very expensive. Okay, let's continue. Returns. Returns out for the calculation of range distance are between the sensors and the surface object, which reflects laser pulses. So here is the formula I promised before. R is calculated by comparing the time the pulse left the sensor to the time each return is received. So here is the formula. R is something we want. In order to calculate R, we need C and T. C is a constant. It's the speed of light. We consider this as a constant. Okay. T is the time interval between sending and receiving the same pulse. Usually it's a very short time, so it's nanosecond. Why do we need to divide this time by 2? Because your pulse, your laser pulse traveled to the ground and return. So the distance should be divided by 2, right? Should be divided by 2. It's a round trip. It's a round trip. Okay, I will just stop here, and I'm planning to use another 1 video clip to finish the content of LiDAR. Okay, see you.